Thank you everyone for coming. It's really exciting to see that many people at the Montreal MLOpt. Today, my talk is going to be maybe a bit shorter than 1 hour, but you know, nobody ever complained about the talk that was too short, so I think that's going to be fine. And to clarify, I won't talk about GANs only, but generative models in general. So if you're into, large language models, that may apply to a certain extent. So what is the starting point of this work? The idea is, who knows the Lion dataset in this room? Great. So usually, I ask this question and a small 10% of the room knows. So for the ones who don't know, Lion is basically the largest open source dataset with 5 billion of pairs of image and text. And actually, the dataset is so big that it's decentralized. Like there is nobody. There is no way to just click on a link and download it. The dataset is a list of links, and you have to download it yourself. You have to basically have a script that goes, queries the web, gets the picture, and you build the dataset yourself. And so the problem is, in some sense, this dataset is the web, and it's dynamic. Like what is on the websites can change, and actually we have seen recently that some people demonstrated that you could attack this dataset. You could buy the domains and poison potentially the data for a few cents, less than thousands of dollars. And so yeah, these datasets are decentralized and are on the web. And so the problem is that what do we see on the web? We see a lot of data that are not human generated. So this is from the Lion dataset. And in particular, what you can see is that there are a bunch of images that corresponds to past iteration of generative models. So if you know, who knows which paper it is?
Big GAN.
Yeah, there is some GAN aficionados. So this is the big GAN paper. This one, actually, I don't know, but Alexia probably has the answer. I don't know from which paper it is. This is the very famous avocado chair generated by DALI, which was the beginning of like, large model can generalize. We ask them to create something that has never been created before. And the design of avocado chair is somewhat convincing. So this is purely generated. This is purely generated. And this is somewhat good. There is also some bad generated pictures from previous models. But yeah, long story short, generated data are all around the web. And when you train your diffusion models on the Lion dataset, you will train ungenerated data, partially. And so basically, what's going to happen is that in some sense, we have this feedback loop where we have generative model. You train them on originally human data because this is the only thing that you have that is available. But then once you have trained the first generative model, you may be able to sample new pictures. And these pictures will kind of populate the web and basically be included in the next iteration of training. Also, I want to say that please ask questions at any time. This is great. We are, for the ones who are in person, we are in person together, and a talk is meant to be interactive. So please interrupt me. This is going to be more fun and more interesting if you do so. So yeah, that's kind of the starting idea for this work that has been accepted at iClear. Congrats, Quentin, or congrats, Damien, I don't know anymore. No. Congrats, Quentin, for leading this work. And yeah, it's a joint work with Joey, Alexandre, who was doing an internship at the time, and Marco, who is here. So yeah, the idea is the following. Let me get back. We will try to study. Basically, we will propose a sort of toy model for the impact of synthetic data on the training. And this model is the following. We have some data, we train a model, we sample, and we use these new samples to retrain the new model. And in particular, the theoretical framework we will use is maximum likelihood estimation. So this is usually a standard way to learn generative models. And so because a large fraction of generative models are trained via maximum likelihood, we will assume that we consider this class. And so the step 0 in this setting is to start with a model that has been trained to maximize the likelihood of the data. So we have a parametric model. So you can think about this as your neural network, your GAN, or your diffusion model, that has some parameter. And you want to learn the best parameter that maximize the log likelihood with X samples from the data distribution. So far, so good, I hope. Don't worry, it's going to get a bit more tricky. So what is the idea? You have the data. You first train your generative model. You get this p theta 0. You sample new data from now not the distribution p data, not from p data, but from p theta. And you will reuse this as your new data set, or at least a part of your new data set. And the question is, what if we repeat this? What will happen? Will we observe a collapse of the model? Or will we maybe get an improvement or at least convergence? So far, so good? No questions? Okay, great. So, okay. As an illustration, let's see what happens with Gaussian. This is nice. Gaussians in 2D, we can visualize them. We can see the distribution. We have some good intuitions. So what happens? So we start with our data set. So we also assume that the data set is Gaussian. It's a very toyish case. So we sample from this a bunch of data points. And so learning from these samples basically means that we want to learn what is the mean, the best mean, and the best covariance to fit this data. So that's it. We do the learning step. We have learned our mu0, sigma 0, which is the equivalent of the theta 0 from the previous slide. And then we sample from this new generative model. So now we have learned, we sample the new ones, and we get some new data. And what happens? And we can summarize, we can rewrite this mathematically as having the sampling step, which is basically sampling from the previous parameters learned, the mu t, sigma t. And then the learning step would be computing the empirical mean and the empirical covariance from the data. So very simple things. We sample, we learn the mean and the variance, and we keep doing this. So question for the audience. What do you think will happen in that case?
Bias.
So converge with a bias?
Yes.
Converge where? To what? To something?
Probably to the mean is something that depends on the variance.
Okay. Interesting.
That's a random walk.
Yeah, it has the vibe of a random walk to a certain extent. So and it actually is, but it's worse than that because we're gonna end up somewhere to a certain extent because the variance is gonna actually collapse. So it's working, but you kind of you're gonna estimate. Your estimation of the variance is going to be smaller and smaller. And at the end of the day, we will sample only a point. And if you sample only a point, you will estimate this point as the mean and the variance as 0, and you will be a fixed point. And so what we were able to show is this. Yes, Simon?
What if you regularize the maximum likelihood?
So what if we? So what would be the regularization?
Well, so you. Good question. You don't want to have overconfident Gaussian, so you could have like something that you penalize away from the identity for the covariance or something. So you shrink towards the identity. So then what would be the dynamic?
Oh yeah, so you would penalize to get close to the so if you you would force the covariance to be close to the identity. I think that would be okay in that specific case. I think you would be safe. But wait, I have other fixes. Do you? But yeah, I'll need to think about it. But it's very quick intuition. You should be all right. But I mean, you would have a strong bias because.
Well, ML is always overconfident, right? So that's the problem.
But yeah, I'm not sure it's about being overconfident because at the end you get something that is it's like the distribution is slowly shifting.
If you had infinite data at each time, you would not have this problem.
I mean, if you have infinite data at each time, it's a bit infinite data is in the following slides.
What's alpha? What's alpha?
It's coming. Alpha is basically okay. I hidden the alpha. Alpha is something smaller than 1. That depends on n. So it's something strictly smaller than 1. It's something like n over n plus 1 or something like this. So there is a Jose, I think, Ryan, and then Adam.
Just a clarification question.
I said Jose first.
Oh, sorry.
You have to throw the dice. Throw the dice. Where's Jose?
Give it to me.
Oh.
I was so excited.
Yay! Target.
Well, one way to regularize is not to remove all the data together. Like you can keep some of the old data and you can keep some of the new data. But right now you're just keeping all the new data, right?
Yes.
Without adding the Gaussian, the isotropic.
There is good questions are questions I have an answer for, and great questions are questions I have a slide for. and I have a slide for you, Jose.
Thank you. Sorry if I could see.
Interesting.
It was just a clarification question. Like, is it the learning step all previous data? I guess based.
Yeah,
on
you only learn on the previous.
but all of the previous data, not just the previous generation.
Here it's just the previous generation. I agree that you could extend this as like a mixture of all the previous data. It starts to be a bit more complicated because it depends on how you mix and etc. So I guess this is like the simplest setting to study. But you could extend to like a mixture of all the previous, but then it's a sort of regularization to a certain.
But that wouldn't have this problem, right? Or your intuition probably would say you wouldn't have this problem.
You may have this problem too, if it's an uniform. Yeah, I mean, open question to prove, but I'm not sure it will fully solve the problem. Simon's thing will solve the problem, but it gives a biased estimate.
I think.
And anyway, the point is not like, I mean, I haven't found it's not to show you the best algorithms to learn Gaussians. Like, just to be clear, it's just a case study to understand what happens when you iteratively retrain on your own data.
So I think in this case, what will happen is that unless you up-sample the original true distribution, at some point there will be too much fake distributions. It will keep shifting, being more overconfident problems. It might still work.
But the shift will be slower. I think you may not get exponential convergence to 0. yeah, that's why I try to be a bit cautious with the statement, but I feel like it should be similar. Yeah, it should be similar, but harder to analyze. Alessandro? No? There was Adam. There was Adam question.
Some online questions.
Okay.
So
You good, Adam? So what is the frequency of sampling? I'm not sure I understand this question, but you at each time step you sample n data points, you learn, and then resample n data points, and this is like this sequential thing. Would this variance collapse still happen if the generation is conditional? Meaning the cluster needs to generate across many clusters. That's a great question. We did a similar experiment on mixture of Gaussians, and same thing happens. It's just you don't have closed form anymore, so it's a bit harder to analyze. We also have great experiments on real world data sets like CIFAR, where actually also there are collapse. Actually, we try to fight the collapse, but yeah. Sorry. We also have experiments on CIFAR and there is collapse. Alessandro?
Yeah, I just wonder whether sorry. I just wonder whether the dimensionality of the ambient space affects this
Is 2?
result.
What is the dimensionality of the ambient space?
I was wondering if this is
So sorry. So this is arbitrary dimensionality.
Okay, so it doesn't depend.
But for the sake of visualization, I showed you.
Yeah. Okay.
There was a question. Yes.
It was.
You ready?
It was almost the same question, but because someone mentioned the connection to random walk and random walk in 2D and 3D is quite different. So does it generalize to higher dimensions?
Sorry, can you speak slightly louder?
Yeah, so just because someone mentioned there might be a connection to random walk, but random walk in 2D and 3D is quite different, I think. So that's why I'm wondering, like, how does this generalize to higher dimension? Like, does the low flux still happen? It's the same question.
Okay. So first of all, it generalized to, it's arbitrary dimension here, but the connection with it's in the questions at the end. I think the one open question is to generalize such a result for arbitrary, I would say, family of generative modeling. So if you take an arbitrary class here of p theta, it's not Gaussian, so you could think about mixture of Gaussians, or you could think about any exponential family, or even something parameterized by a neural network. The question that is still open is, can you show a similar phenomenon that like the variance of what you're estimating is getting down to 0? And it seems that it's connected to random walk. Like we had tried to think about it with a perspective of random walk. It's clear that once you have collapsed, you cannot recover because you generate only one point and you learn this point and that's it. But yeah, we haven't been able to prove anything. We actually have a counterexample where it's not collapsed. The variance is not collapsing to 0, but it's a bit pathological. So I'm suspecting that with the right set of assumption, I'm still hopeful that you can show that the variance goes to 0 with the right set of assumption on the family. Nicolas.
So, and I think that's pretty much super related to what you just said. So this is super related to properties of the KL divergence. It's mode seeking, and so you're going to latch onto one mode, and so your variance is going to get smaller and smaller. So do you expect, like, if you were to revert to KL or just standard alpha divergences, do you expect the same thing to happen? I would imagine the variance below to infinity was the other KL, for instance. And maybe it was alpha equals 1/2 to stay relatively stable.
I guess that's that's a very fair point. Yeah, we decided to focus on log likelihood maximization, because we had to start somewhere. But I think that's a very valid point that we could just, I guess, generalize this to any F divergence and see whether or not it does change something. If I try to think quickly about the theory, yeah. So our work is about showing that things are stable if you do the right thing, and I think this would work for any F divergences. But yeah, for the instability question, that is a bit more open-ended and I guess also probably harder to tackle. Yeah, it will depend a lot on the divergence because we are kind of in the limit case. Yeah, maybe I don't. Let's talk about this offline then. But you are completely right, and I really like this suggestion. Damien.
Okay, maybe that will be the last question.
Thank you so much. I asked you to ask question. You did it. I think you're great. Please. Let's continue like this. Okay, so we were at this warm up. Great. So just to give you a visual. Oh, this is really not working. On my screen, is way much better. But you have the value. So yeah, so you see the Gaussian collapse, and once you have learned a Gaussian that is that flat, and you will sample from it, you will actually it's going to be too late. So that this illustrates the phenomenon. You still can see that the collapse is quite slow. Okay, so yes, Janice.
Quick question. Does this decay of alpha? So you said that alpha depends on n.
Yes.
What's the dependence on n? I guess with big N, alpha becomes bigger also.
As n grows, alpha gets closer to 1.
Yeah. Okay.
So yeah, in some sense, if you had an n that was increasing with the time steps, you could compensate the fact that you go to 0 by using more and more data, and you could have some sort of stability. But if you sample a fixed amount at each time step, you will converge to 0. Mm-hmm. Okay, and this was the points that were made in all these two papers that were previous works, where basically they were the message from these two papers was, that's terrible. We are doomed. Training on generated data makes model forget. We have collapsed. Self-consuming generative models go mad. So here you see a GAN trained on its own data, and you see that the quality of the generation decreases. I don't know if it's super clear for you, but if you look at the patterns on the cheek, you can really see that some artifacts are appearing and are becoming more and more clear. So yeah, these two papers were like have had a message that was quite pessimistic with respect to the generated data, and here we come, Jose. Our message was actually we will reuse some of the original data, and so we should not consider that we fully retrain ungenerated data, but we will mix between real and fake data. And the question now is like, will we have the same conclusion if now we have this regularization, which consists in, a sort of regularization, which consists in partially training on real data. Okay, so the setting we will consider that generalize these two, the two previous points mentioned is the following. So we have a generative model at time step t. There is also a question that I will read at the end of the slide. So we have a generative model at time step t that generates your data. And at the following step, we will maximize what we call augmented likelihood. Maybe it's not the best name, but this likelihood with this additional term that depends on our data. So before, we were just maximizing the likelihood that was depending on the previous data. And now we have a mixture between real data and the generated data at the previous time step. And what we have here is a coefficient lambda that says what is the relative fraction of generated data and real data. So an equivalence way to say this is that we will train on n data. If we train on n data samples, real data samples, we will also train on lambda times n generated samples. And yeah, the question we want to ask now is like, okay, when lambda goes to plus infinity, we only train on generated sample. But what happens when lambda is finite? can we prevent collapse by having some real data in the loop? Does this make sense? Cool. Thank you. So yeah, the algorithm is really simple. You don't have to read all the lines. I think, yeah, okay. Like what really matters is the following. This is this loop where you generate synthetic data, you generate lambda endpoints with your previous generative models, and then you train the next one on the union of the synthetic data and the real data. Now I need to answer the question. How much does the ratio of synthetic versus real affect the instability conclusion in these two examples? So I can tell you that in the two example, if you add real data, you will remain stable. Once again, great question, because I have a slide for here. So now if you do 50-50, so on the left, this is what you see. You saw fully synthetic data, and on the right, you are now mixing, training half on real data, half on synthetic data. And what you can see is that the right one is not collapsing. I hope you are visually convinced by that. And we can also actually prove it theoretically. The contrast between what I see there and what I saw there is quite interesting. All good?
Yeah, so that means that technically for the half synthetic data, you have also less data point because your real data is limited.
That's a very good point. In order to do a fair comparison, you need to use the same data set size. How do I do this short? The thing is, with synthetic data, you can generate way much more. It's way much cheaper, so it's not really a one-to-one comparison. For this specific plot, I think it's the same number of synthetic. I mean, the data point the both sees is the same. So
yeah, but that means you increase the number of real data on the right as well.
I mean, on the left there is 0 real data.
Yeah, so you just put synthetic data in it, but you increase it over time. And on the right, you're increasing at the same time synthetic and real data. That's correct.
Yeah, so the first one, you start with a model that has been trained on the real, and then you forget. You just train on your own data. And on the left one, you train the model on the real data, and then at the following step, you generate and makes a mixture between real and fake, and have.
Okay, I see.
I will come to exactly how we did for the experiment on the real data set. What we try to do a fair comparison is that each model will see the same amount of real data. So you could basically, with generated data, you can argue that you can generate very easily. So you could easily see way much more generated data, but every model will see the same amount of real data with a different augmentation with generated data. Thank you. Do it.
Just a quick question. So on the right, you're stable, but you're stable with a lower variance than the true one, no?
Is the variance lower than the true?
Lower, yeah, on the right. When you use half synthetic, will you be underestimating the variance and stabilizing, but at a lower value?
Stabilizing. Maybe.
We can talk about,
I'm not
about
sure.
this after. I think so.
Yeah, maybe. Yeah, I mean, yeah, I'm not sure.
So the question was, you start from a penalized objective with the lambda and the the mixture that you have, but then from that you argue, well, this is equivalent to training on this fraction of real and this fraction of fake. But you could also just train on any fraction, pick whatever number of fake you want, and then just use the actual penalized objective. You could compute the sample expectation and the real sample expectation of fake without having to rescale the number of data points. What was the motivation for actually, getting into changing the number of data points that you have for real and fake instead of using the penalized objective, which is what you start from?
I mean, usually you're limited by your real data. So, if let's say, in CFAR you have like n data sample, you cannot do better, but then you can generate potentially a lot. And then the question is, depending at which speed you generate, will you or won't you collapse? That was the rationale. I don't know if it makes sense.
No, I didn't.
Like, when you populate the web with like generated data, the web is growing with real data, but like we've also fighting against generated data, and like in some sense, it's at which speed like both are populating the data set. That would be the rationale.
Maybe what I can see is that the way you construct the entire data set, you might have like the composition of the different mini batches will be different, and that's going to give you different dynamics. Because otherwise, you could just handle this with the equation that we see there. Compute an expectation in real, compute an expectation in fake, and then weigh it by lambda. That's not what you're doing.
So what we do in practice is like n real, lambda n real, and lambda n fake.
It's not the same.
What do you mean? This is why I'm confused. It's like, up to the finite sum aspect, it's the same.
So basically, on the left, you have the expectation with an empirical distribution. And on the right, you have the expectation with respect to the true distribution p theta t. And having a lambda between them is not the same thing as sampling lambda n and working with that. This is a noisy estimate of this objective.
Yeah, up to statistical noise, it's the same thing. And like the expectation with respect to p theta, you also need to sample with respect to p theta.
Well, it depends what you're using, right? But here you know what p theta is.
Yeah,
the other one, you only had data. So you might have just done the analytic expectation for the Gaussian, for example.
Yeah, for the Gaussian you can, but like for a diffusion model in practice, you will also sample. So you will have finite sum for both. I agree. I agree that statistical noise is a tricky one, but I think what's interesting in our framework is like we try to kind of disentangle the two. And I think our conclusion, when lambda is between 0 and plus infinity, but when lambda is finite, we have stability, and the statistical noise should not affect that. Okay, so and so in a more interesting case, maybe you asked about mixture of Gaussians and everything. So we start from the ground truth. We have a mixture of 8 Gaussians here, and we train, I think, a normalizing flow. So first step, you see the normalizing flow is quite good at matching the distribution. And the more you will retrain on your own data, you see really this mode collapse, where actually each mode is collapsing into itself, interestingly. While when you train and re-inject your data, the real data distribution, you maintain this stability. And this process was done really using the algorithm I mentioned. So with finite samples, we sampled n real data points, and at each time step, we sampled lambda times n fake data. Yes, Yanis.
What is the value of lambda?
That's a very good question. Here, the value of lambda is 1, I think, for this experiment. So it was as much real as fake data point. Mm-hmm. We will have a result in the theory that says that if lambda is small enough, you have stability. So if you have enough real data against fake data.
And is there any hope to get concrete numbers for actual applications? What would the real lambda look like?
That's a very good point. I think we could discuss it once I show the theory. Thanks, Yanis. Cool. So the theory we try to propose is a local analysis for stability. So the idea is that we are in this regime of a pre-trained model. So theta 0 is trained, is the parameter of the model trained on the real data. And what's reasonable nowadays is to assume that our generative model is good. It's like generating like really satisfying samples. And so what we will assume is that theta 0 is close to the best one, meaning the model that actually is the best within your class of functions to fit the data distribution. And we will also assume that, it's gonna be just below. Yes, here. It's what I meant also is that the generative model is good, that the best generative model is close to the data distribution, meaning that you are generating a good-looking sample. This is what I meant, sorry. And we will characterize how far is the generative model from the data distribution with this epsilon. And so what we will see is that if epsilon is small enough, so meaning that our original data generator is close enough to the data distribution, we can afford a big lambda. So like the more the original sample, like the original fake samples, the better the fake samples are, the more stable you can be, which makes sense. Okay, so that's the idea for the theory. So we initialize with a model that is close to the best one you can get, and the best one you can get is generating good-looking images. I hope stable diffusion and everything convince you that this is realistic. Yes, Simon.
Yeah, just clarify the close of theta 0 is in like distribution.
Yeah, that's a very good question.
Because
so that's the weakness.
Norm could be anything.
That's the weakness of our analysis. We will analyze everything in the parameter space. So we will assume theta 0 to be close to theta star in parameters, L2 distance. And one of the follow-up we absolutely want to work on is to do everything in the distribution space. And I believe this is true. There is a hope, but we haven't proven it yet. So yeah, and the intuitive result we will have is that under some regularity assumption that I think I have time. I will have time to explain, give you some intuition. If we start close to the best model, basically we will stay close to this model. So meaning that we will not collapse. So we initialize, we have learned from the data, we are close to the best model within our class. And if lambda is small enough, if we start close enough and lambda is small enough, then iterative retraining is stable. This is the kind of the main takeaway of the paper, meaning that when we will train on our own data, we will get actually closer and closer to the best model within our class. Yes, Ariane.
Is stability always, does it mean movement? No.
Very good question. The question was, is stability mean improvement? No. Stability means stability, meaning that you don't collapse. We are in the infinite data regime. So in some sense, okay. So in the infinite data regime, if you don't start with the best model because you have some optimization error or whatever, actually it could mean improvement because you would like iteratively retrain on infinite data and get closer to actually the best one. But if you already start, putting all this aside in practice because you have statistical error and you are not in the infinite data regime, what we observe is that you're stable in the sense that you don't diverge, but you actually, it seems that you stay close at a point that is maybe slightly worse, which is connected maybe to Charles' point that you converge to something that is not exactly the covariance of the data. You have a slight bias due to the iterative retraining. Ryan.
In the toy example, the variance estimator was just divided by n.
It's divided by n-1.
Oh,
very good question. So Ryan, you spotted the thing that I hope nobody spotted. So
because MLE is biased. Right?
Exactly.
Downwards.
So exactly. So actually, for Gaussian, maximum likelihood estimation was too easy because you divide by n, and so the variance actually is really converging to 0 too fast. So we try to solve a harder problem than what we had to. By dividing by n-1, the variance is converging less fast to 0. If we were to use the true MLE estimator, it would be easier to show that it converges to 0.
So the synthetic examples use an unbiased estimator of variance?
Yeah.
But isn't that weird? It still converges to 0, like intuitively?
That's the beauty of it. That's why it's
like it's like you're always adding an unbiased estimator. Like, why should that?
I think the intuition is that you know, in the sampling process, you may get unlucky and only sample points close to the mode. But then you will learn from these samples, and so you learn a very conservative variance, and you will get stuck in this vicious circle. Once the variance has decreased, you cannot relearn diversity.
So here you said the theory was for infinite sample.
Yeah, so there is two things. There is Gaussians without.
Yeah, but so your theory says nothing about the Gaussian example, because the Gaussian example with infinite sample would stay stable.
So
because it's a consistent estimator.
Yeah, so with infinite, so that's the problem. For the instability with infinite sample, everything is a fixed point. You sample from your generative model, and then you learn yourself because you are the best. You know, like yourself is the best way to fit the data you generated. But what's interesting is when you start to, so for instability, you need to take into account the finite sample aspect. But for stability, you don't. So that was our point. So there is two things: instability for finite sampling, and then stability with infinite sample is okay. And we have a bit of theory for the finite sample and stability, but it's basically just a perturbation analysis of the infinite one. Okay, so we have 15 minutes. I hope you are still have a lot of energy. I tried to give you some intuition about the proof. I think it's a bit short, so maybe I'm gonna try to go quite quickly. But what's the idea? The idea is the following. What we have is that the next point, theta t plus 1, as I said, was the maximizer of this regularized maximum likelihood. And what you can see is that basically theta t plus 1 is a function of theta t by being the maximizer of this function. And so the analysis boils down to Taylor expansion, because we want to do a local analysis, meaning if we start close, we stay close. And the main idea is the following. If we have theta t plus 1 minus theta star as a L2 distance, we know that theta t plus 1 is the result of the maximization as a function of theta t, and we know that theta star is a fixed point. If you had the best model, and you would learn from the data of the best model, you would learn yourself. So basically, then you can do a Taylor expansion of G, and you know that the distance between the t plus 1 step and the solution is smaller than the norm of this operator, of the norm of the Jacobian of this operator, multiplied by the distance at the previous time step. Here it's a star that is missing. So I hope it's good for you. And the trick here is like it's completely non-trivial because we need to differentiate through this argmax function. Chance is we know how to do this. And I'm going to try to give you a one-slide intuition on how to do that. And please bear with me. So what we do is we just use the definition of G theta being the maximizer. So it means that the gradient with respect to theta star of this function at tested at G theta is 0. It's the maximizer, so the gradient is 0 at the optimum. So this is just what's written here. I took the gradient with respect to theta prime here and there. Don't see, yes, you see my arrow. I took the gradient with respect to theta prime and tried specified it at G theta, evaluated it at G theta, and we know it's 0. And now it's the standard trick in implicit differentiation. We know this is true for all theta. And so if I differentiate this function, this equality with respect to theta, I will get, by the chain rule, this complicated equality. And in particular, I got the differentiation through G because I know that this function is applied at G. If it was too fast, you can just trust me. What you get at the end is the following formula, thanks to standard tricks, where we know that the Jacobian of the operator has these specific forms that depends on basically the Hessian of the log probability according at G theta according to the data distribution and the generated distribution. And what is the intuition? If you assume with me, you're still with me, and you assume that I'm not lying to you, and that this formula is true. What is the intuition? The intuition is very simple. When the generated distribution is close to the data distribution, these two matrices are almost equal. Okay, but if these two matrices are almost equal, we can simplify this formula because it's basically a matrix inverting itself, and we get that the Jacobian has this form of lambda identity over 1 plus lambda. And what you can see is that this Jacobian has eigenvalues that are all smaller than 1. They are all equals to lambda over 1 plus lambda, which is like in norm smaller than 1. And that's thanks to the fact that lambda is not plus infinity, that we will actually have this contractive operator that will make us closer to the solution. If it was too fast, this is the end of the proof sketch. I'm sorry, I was lacking time. I'm gonna move over this. Yes, Jens.
Really quick. So in your analysis, do you quantify the effect of A and B not being exactly equal?
Of course. So in the analysis, because we do a local stuff, what we will ask as an assumption is that we will ask for this function of x to be Lipschitz. So we want the Hessian to be Lipschitz with respect to x, and we will leverage this to actually do some perturbation analysis. So even when they are not equal, because at the optimum they will be very close, we will ensure that in the neighborhood they will be very close, and so that in the end this matrix will be equal to that, which we are happy with, plus some error terms that we can control thanks to the Lipschitzness of the functions. So that's actually exactly the spirit of our assumptions. So some smoothness assumption, and also a regularity assumption with respect to the parameter, which basically says that the parameter we are looking for is at a strict local maxima. Otherwise, it's complicated to find it. It can be arbitrarily far from where we start. And long story short, what we get with this is this theorem, and I'm going to focus on just text here. The condition we have is that lambda times a certain quantity has to be smaller than 1/2, which can be interpreted as follow. If we do not use too big proportion of synthetic data, meaning if lambda is not too big, and if our initial generative model is close enough to the data distribution, so epsilon small, if I remember that epsilon is the distance between the real data and the best you can generate with your generative model. So if these two things, if epsilon is small and lambda is not too big, then the condition holds and we have stability. So what we extract from the theory is that there is a condition for stability that exists. Then the question is, as you ask, Yanis, what does it says about the practice? And I think it's also connected to the question of Luis. What happened in a case with which we don't know lambda? There is a lot of things we don't know in machine learning. You know, we don't know the Lipschitz constant of the gradient, and we try to optimize hyperparameters. So I would say in practice we will not know lambda. There will probably be a way to estimate it. I would say though that this theory is suboptimal, and we are suspecting that we should have a lambda times epsilon. So if you start close enough, you should be stable for the closer you start from, the more you will allow for a lot of synthetic data. And I can tell you that we had a breakthrough today in the proof. We're able to prove it, but it's not published yet. Yes.
So unless I missed something, there is nothing in your proof that relies on the lambda fraction of the data being synthetically generated based on your previous data. It's all about stability. So it could be coming from a different source altogether.
No, it has to because of the yeah, you really use the fact that you differentiate g theta with respect to theta. So in all the analysis here, you know, so yeah, up to there, this doesn't take into account the fact that, you know, this p theta could be any source, but once you do the implicit differentiation step, you use the fact that this comes from theta to compute the gradients and to get the final matrix. Okay. Otherwise, you don't have the formula that I mentioned.
Okay, I see. So this does not trivially apply to the case where you mix with new sources if they're close. If I take a new source that could be real, could be synthetic, and I do this kind of mix, and under the assumption that it corresponds to your new source can be mapped to a theta which is close enough to your theta 0, I wonder if we can say something similar.
Using the dynamics.
Yeah, I guess the thing is like you need to generate, like the overall question is what happens with the data. You know, you collapse because you train on your own data that gets worse and worse. So what is this?
So yeah, you need to close the loop.
Stuff, you cannot collapse.
I see. The loop is not closed. So
yeah.
Okay.
So if you don't like theory, it's time to wake up. I have some experiments for you. So we tried on, I think this is a, sorry? Yeah, a flow matching, thank you. On 2D dataset again, because it's nice, we can see visualize the distribution. So the 2-moon dataset and similar patterns as the mixture of Gaussians. If lambda equals 1, you're stable. If lambda equals plus infinity, you collapse. And then we tried on some real data. I lied to you, actually. We also tried on real data because we did it on FFHQ. So that really looks like something somewhat real. Some people argue that it's still cheating because the background has been post-processed, but that's another question. And yeah, we have like basically the number of iterative retraining on the x-axis. In the y-axis is either without synthetic data, so it's the baseline. It's basically, you know, the model trained on the real data. Here it's half synthetic, half real. You remain stable. It's the same random seed, so you see you basically have learned the same model. You're not diverging. But if you train on fully synthetic data, you really see this slow collapse of the generation. Yeah. And then we did it also on CFAR. And what we plot now, instead of having some visual argument, I mean, I convinced you by picture here, and here I will convince you with some quantitative metric. So we have plots. The more blue they are, the more the less synthetic data you use, and the more closer to red, the more synthetic data they use. And in particular, the red one is the one that use only fully synthetic. So only fully synthetic, you really see this very fast divergence of the FID. So for FID, lower is better. 2 is a very good FID. Back in the days when we had GANs, the best FID was 10. So we have I mean, around 10. Now 2, I mean, the state of the art must be 1 point something, but 2 is very reasonable. And what you can see is really that as long as you reinject some real data, so up to lambda equals 1, so half, you remain stable. And to answer your question, Ariane, you see that here there is no improvement by doing iterative retraining, but you stabilize. You don't diverge and collapse to something bad, but you kind of have a FID that is somewhat in the good range of acceptable. So you don't improve, but you don't collapse. And here are precision and recall are just 2 metrics that are a bit more specific than FID. Precision is the quality of the image, and recall is the diversity. And for precision and recall, higher is better. So once again, you see that collapse for the fully synthetic and stability for the two other ones. Yes, Yanis.
For this example, have you tried to find the threshold for lambda at which you lose stability?
That's a fantastic question.
Because you have a slide?
No, I don't. I didn't say a great question. I said a fantastic question. The fantastic questions are the ones where I'm embarrassed. So it's hard for diffusion model because as lambda, okay. So to do an apple-to-apple comparison, we give the same amount of real data to all the model. So n is fixed to 50K. So if you want to have now lambda times 50K, you need to, for instance, lambda equals 10, you would need to generate 500,000 generated data per time step, so per. And with diffusion models, this was too expensive for us. So we stopped at generating 50K example per time step. But virtually you could do it. I would have loved to be able to do it, but it really was out of our compute budget.
Maybe a smaller experiment with a subset of the data?
Yeah.
Of the true data?
Yeah, I guess we could have done, or maybe just a 2D experiment on, yeah. So the problem is like, okay, another problem is in the theory, you want epsilon to be small because if epsilon is small, lambda can be bigger. But if you start to train on subsets of the data, you know, you are kind of not in the real regime that is interested in where you are close to the data distribution. So, I mean, I agree with you. That's a very fair question, and we don't have it for compute reason. Yes, Yanis again.
And one more, real quick. Should we interpret the last plot as a potential sign that you might gain in recall by using a tiny lambda?
I think, actually, I don't think you should. Because I think we have opposite stuff for precision, if I remember correctly. So on EDM, I felt actually we were gaining in precision. So locally, you were actually generating better pictures because you were focusing on the good pictures you were generating, but your recall was dropping. So my intuition was more than we were gaining in precision until we would collapse. Which is, you know, here it's interesting because for the few first step, fully synthetic improves precision, for instance. But this one, yeah, that's true. We win a bit about recall. Yeah, I'm not sure how I would interpret this. Yes, Sophie.
Related to that question, I guess you have no estimate of what the variance is of those curves, like because you only did a single seed run, right?
Maybe I can take this one.
Yes.
So like for the FFHQ experiment, it's like 40 GPU for 1 week.
Yeah, no.
So there's no variance.
We have a lot of, yeah, we have them for a lot of different values of lambdas, and because it's somewhat continuous with respect to lambda, you have a sense of the fluctuation, but I agree. Simon, I have a plot with error bars for you in 2 slides.
Yeah, just to clarify, you said epsilon needs to be small, but epsilon is the distance to the maximum likelihood estimate on the empirical distribution. Right?
It's the no, it's the Wasserstein between p theta star and p data.
Yeah,
so
p data is the empirical, not the true one.
No, it's the true one.
Why? You have a fixed data set. Why do you care about the? So it's just p data, which is why you can have n equal to 10 and it's still fine.
Yeah, I'll think about it, but I guess you just need memorization. I think it's, yeah, we were more like in the infinite sample case. Okay, you're right. I'll think about it. Okay, do I have the slides for you, Sophie? Or is it hidden? I had the slide in the past. I guess it's no.
That's the question.
I have an appendix for you. I'll pull out the slide after the conclusion. So yeah, the conclusion was that while previous work seemed to argue that retraining on your own data was doomed to fail if the original dataset is forgotten, that they called collapse, and they showed experimentally. We have some theory about this, and it seems to be it's true if you don't re-inject real data. And one open question is to prove these results, prove that variance is collapsing in general if you don't re-inject real data. But the point of this paper was to argue that if you add to the original data, you add the original data set to the generated data, you maintain stability under the condition that you do not use too much synthetic data and that our initial generative model is close enough to the data distribution. Finally, there is a lot of open questions about actually improving the sampling process. So in the real world, the data that are in the web are just not random samples. They have been curated by humans. Yeah, the avocado chair is a very good example. People put it because it looked good. Most of images that don't look good are not in the web. So there is still this open question about human filtering generated data. And so maybe we could stay stable, only adding the assumption that generated data are filtered. And better bounds in terms of open question would be working in the distribution space and having a better dependence on lambda and epsilon. On this, thank you very much. I'm 5 minutes late. I apologize, and yeah, happy to talk more with questions.
So it's time for a few questions. Right in the back.
Thank you. I think I'm going back to the question about improvement. Why should I or anyone care about the stability? Because this seems like a problem that you created and then talked about it. But I don't think it's. Why is this done in practice or in?
So I mean, first, I guess it's our job to create problems and solve them. But it felt to me that it was connected to a very important question of understanding what is this dynamic long term of like having what happens when you train on data you generate.
But does that happen if you filter the data or?
So that's the first step. I agree. The point is to keep building on this. We try to show that in the simplest setting, there was still a hope for stability while injecting real data. And I believe the next step would be to show that there is still stability filtering the generated data. So yeah, the goal is to provide a framework to understand this. And I agree that it's not exactly representative to what happened in practice, but the goal is to get closer and closer as we improve our understanding of the problem. Sophie, to answer a question. So we did error bars on, I think this is the 2Moon data set, where we could actually do it with a lot of samples. And actually, for this one, I think the models are so good that they are really matching the distribution very well. And so you really actually see even improvement because lower is better for the Wasserstein distance. And yeah, so fully synthetic diverge and lambda 0.5 or 1 remains stable.
I have a question. So I'm curious in the Gaussian mixture, for example, if your Gaussian has different variances, do they still each collapse to their own mode? And my connection to like real life scenarios, like we're saying machine learning could enhance human bias. Do you see that happening?
Can you repeat the second question only? The first one I got it.
The first one, so the connection to like a real life scenario could be saying like machine learning models enhance human biases.
You mean when you filter?
No, when your two Gaussian model have different variances, say one is like stronger than the other or something, like do they still each keep their own modes after
Oh yeah.
certain
So
iteration.
when you do iterative retraining on mixture of Gaussians, I think if I remember correctly, they keep their own mode, but the variance is going to 0. Unless you're very, very, very unlucky. So I guess, because you sample each of the Gaussian with probability 1/2. In a very, very, very unlucky event, you sample only one of the modes. Because you sample n times, there is like 1/2 to the n probability that you only sample only one mode. And once you have sampled only one mode, you cannot recover the second one. So in practice, it's very unlikely to happen, and you would have the 2 modes. About enhancing human biases, yeah, I guess it goes back to Nicolas' point that it's mode seeking. So it's forgetting its diversity for sure. I mean, that's the kind of the problem of this stuff is that when you do generative modeling on your own data, as soon as you forgot an aspect of diversity, you cannot reinvent it. And this is the mode in the mixture of Gaussians, but this could be some other things in real world application. Yes, Sophie?
Why do you say you can never rediscover it? You could just change your sampling procedure to sample a higher variance, right? Like you could.
But if you are unlucky, when I say forgot, it's like if you're unlucky and you don't sample a mode, it's not in your data anymore. So you will learn your new model will try to match this new distribution that doesn't have this mode. And then you will never sample it anymore, most likely, because you have learned not to sample it. That's kind of like the interesting tension and phenomenon with this thing. Timo?
Yeah, so I guess the idea here was to answer the question in the back, which was that there's this thing happening of people putting stuff in the web. So and people said it's a problem. So now you say, okay, well, it's not always a problem. Let's understand that. But what about the other way around, which is indeed to improve a model through data augmentation? Have you thoughts on this?
Yeah.
In particular, here you had improvement. Is it because at the beginning you were
within
far?
bar? Yeah. I mean, no, so this is lambda equals 0, but like they are all comparable.
Well, the 0 is worse than best.
No, the 0 is lower is better.
Yeah, so the one on the left
The
is higher than the one on the right. Bottom curve.
What does it mean to retrain when lambda equals 0?
I mean, it's statistical. It's statistical uncertainty. You resample from the data distribution and you retrain. I mean, it
just continue training.
Yeah, it's like because training is not finished sometimes.
Okay.
It's like you have early stuff.
You don't resample when lambda equals 0. You have your original data set.
Yes.
Right?
Yes.
And it's fixed.
Yeah, but this is mixture of Gaussians here, so you can.
Yeah, you can resample.
We allowed ourselves to resample the mixture of Gaussians. We could. Yeah.
We have seen more data.
Hmm?
And do you warm start from the previous parameter?
Yes, we always warm start from the previous parameter.
So then you have seen more data.
That's a very important point in all these experiments. I was wondering if anybody would ask. Otherwise, I was like, maybe I will not mention it, and it's okay. We always warm start from the previous iterate. This is super important. Even in theory, everything works because you have this local aspect, and if you don't warm start from the previous model, you lose this local stability property. Ryan?
I couldn't help think of like time step 2, like in a toy example, when we want to find the variance estimate on the generated data, like the MLE variance, like that itself is biased. So like if we can correct that bias, would that be a different way to fix this problem? Bias in the sense that because like like when we look at the variance of the generated data, it's not the same variance of the previously data, just by the fact that like the estimators themselves have variance, which injects like bias into the data. So like knowing this, maybe is there a way to like counteract that, have a different loss to remove flexibility. Have you thought about this? Is this a problem?
Yeah, I guess I have thought about it. I don't have any very specific questions, but yeah, there is this big question about how to take into account this dynamical aspect. Maybe you can use previous iterations to correct. I guess there is a lot of freedom to basically change a bit the loss or something like this to make it more stable. Yeah, I don't have any specific.
Like at the first, like we know what the like in the toy example, we know exactly what that distribution of the variance estimator is.
Yeah.
So like we can maybe do something clever with that.
I mean, okay, the point of the first example is to be first a toy example. You know, we know how to fit Gaussians. It's and it's also it gives a really solid example that with finite sampling and iterative retraining, you collapse. It's like a clear example where there is collapse. So that was the point of this first. So of course you can fix it, but that the point is more to show that repeated maximum likelihood maximization will induce collapse. Then you know if you have interesting fix, what would be important is that they extend beyond Gaussians, just like re-injecting the data distribution. Yes, Ariane.
What would be the dynamics if you do resetting or you maybe like have a moving average of your previous model?
So if you have a let's say uniform average over the previous ones, so in the setting where you don't re-inject data, real data, so you retrain but with a moving average, I think we will still have collapse, but the collapse will be slower. Though it will be a bit trickier to show, but yeah, to be seen. I don't have exactly the details in mind. The interesting case is if you re-inject real data, you need to be careful to keep the fraction of real data still relatively the same. So if you accumulate generated data, your fraction of real data is decreasing. So you may have collapse because of that. But if you ensure that you maintain the fraction of real data constant, you're okay. And in particular, I think it advocates for an interesting regulation if we were to do policy making right now, which is if you could add metadata on the web about what is generated by AI and what is human generated, that would be very easy to filter and to set up your lambda, for instance. So which is connected to, you know, like now we have a more and more like ChatGPT generated text. And maybe it would be nice to know what has been ChatGPT generated and what hasn't been. And yeah, you could actually then filter. Or another possible case is you have at home data that you know are safe, real data, and then you could mix with like uncertain data and like your fraction of like solid real data.